All right, so a lot of what I'll show you is certainly not all my work, and so I acknowledge the climate processes team and the coupled modelling teams at the Bureau. All right, so the first thing to think about here is weather versus climate. I was given the title climate prediction, and everyone knows about Lorenz's butterfly effect and chaos that limits day-to-day weather prediction to 1 to 2 weeks. And this is an example of that, showing that limit to weather predictability on the right here, looking at forecasts of temperature for London in 2 different years from about in June. And it's using the E7WF numerical weather prediction model. And the reds are different ensemble members, and I'll tell you more about that later in the lecture. And they're just different guesses or different estimates of what the future will happen in the forecast. And you can see that the blue is what actually happened, the dark blue is what actually happened, and the red is the different forecast members. And once you got out to, in this case, about 4 days, you really had no idea what was going to happen. And then maybe in this forecast here is about 6 or 7 days. And people are still studying the limits to weather prediction. And when we talk about weather prediction, we're talking about this day-to-day variability or even hour-to-hour variability. And they look at atmospheric models, especially models in the focusing on the extratropics, our mid-latitude weather fronts. And it's definitely limited to around 1 to 2 weeks. So given that, why do we think we can predict climate? So, there's audience participation. Does anybody want to say anything? Why can we predict climate? Why can we go beyond this 1 to 2 weeks? There we go.
The mean state's not as affected by chaos as the individual.
Yep. That's a good answer. So when we go further out, we start averaging over multiple days. We don't try and forecast an individual day. Is there anything else that people want to add?
For the long-term climate prediction, the boundary condition will be more important than the initial state factors.
Yeah, that's right. So what's an example of, say, the boundary condition? Yeah, so these limits in the extratropics are usually with atmospheric only models, just looking at the atmospheric variability only. But as you go further out, you start to need to look at the ocean as well, and what happens with the ocean temperatures, the sea surface temperatures. Craig?
What do you mean when you say you can do a prediction?
A skillful prediction. Anybody can do a prediction. This is one that has skill, so that if you do many of them and you verify it, compare it with what actually happened, then you had some skill, say, had a positive correlation. Or relative to persistence or relative to climatology. Yeah, we'll get onto that. Good. So, and the other thing is that there are various modes of variability that we know about in the climate system that influence how these slow variations, which we're trying to predict when we go further out. And the things that I list here are not considered when they talk about that 1 to 2 week limit for prediction of the weather. So, importantly, and some of these things are kind of related to the boundary conditions because they're variability in the ocean, right? What I'll be showing is forecasts from coupled models, and then the boundary condition isn't the SSTs, it's what's going on, say, the input from the sun. We're going to actually be using the ocean as part of our initial condition and forecasting all that variability. So as I go through, I'll say, climate prediction possible because of the existence of climate modes and oscillations, persistence, and trends. And various things that are producing those oscillations or modes are listed here on the left. Some important ones that I'll discuss are the El Nino Southern Oscillation, the Indian Ocean Dipole, the Madden-Julian Oscillation, and the Southern Annular Mode. I list other acronyms further down. In terms of, longer-term variability that isn't necessarily a mode, there's certainly a lot of memory in the ocean, which can be exploited for longer-term prediction. There are feedbacks in the system that can help to provide persistence and slower, longer timescale variability, such as SST circulation feedback or soil moisture feedback. And then there's trends that we can also exploit for prediction, such as global warming, ozone trends, and aerosol trends. And sometimes, this is usually referred to as external forcing, whereas everything here in white is internal variability in the climate system. Because I'm talking about both the atmosphere and the ocean. All right. So, another thing to point out is the difference between climate prediction versus climate projection. So, you probably heard from Julie Arblaster this week, unless she was sick. But did Julie come? Okay. Okay, and she was talking about CMIP, that's the Coupled Modelling Intercomparison Project, and she would have been talking about mostly climate projections, I think, in terms of what happens in next century or later this century under continued release of greenhouse gases, right? And it turns out that the types of experiments, that she was talking about are what are known as climate projections. And that's because they only take into account the external forcing, such as the greenhouse gases, the ozone changes, and the, say, the aerosol changes. Whereas climate prediction, importantly, takes into account the initial condition, what state we are in right now, and as well as hopefully also taking into account the external forcing to get the best possible prediction. So when Julie showed maps like this for this is a particular one from the IPCC Fifth Assessment Report, looking at projected future changes in precipitation around the globe. These were from model runs that are so far out that the initial condition no longer matters, and often they just spin up the model slowly from pre-industrial conditions from the 1800s, and they only provide changing greenhouse gases and aerosols and ozone to make these estimates. They run it out far enough and they average over a big enough time period for which all those modes of variability no longer matter and average out. All right. So the history of climate prediction in Australia is interesting to look at. In the 1920s, that was when the Southern Oscillation, which is an important component of what we now know as the El Nino Southern Oscillation, ENSO, was first realised. And there was a meteorologist employed at the Bureau in Melbourne called Quayle, who in 1929 wrote a paper proposing that that seasonal prediction of Australian rainfall could be done using Darwin pressures. So he was very much ahead of his time. And then it wasn't until the 1970s and 80s that people like Neville Nichols and John McBride and others at the Bureau confirmed the stability of that relationship between Australian rainfall and the El Nino Southern Oscillation, noting that Darwin pressures are one of the components of the Southern Oscillation Index. Then it wasn't until 1989, though, that the Bureau started issuing statistical predictions of Australian seasonal rainfall based on the Southern Oscillation. And then in the 1990s, they started to incorporate the effects of the Indian Ocean in those statistical predictions. And then it wasn't until 2002 that we started running climate models or dynamical ocean atmosphere models to try and predict the climate. That first model was called POAMA. And initially, in the early 2000s, we only issued forecasts from that model of the Pacific sea surface temperatures, that is of, say, forecasting El Nino. We still use the statistical model for predictions of the rainfall and temperature over Australia. And then finally in 2013, with POAMA 2, it becomes operational, and for the first time, the Bureau issues seasonal outlooks for Australian rainfall and temperature with a dynamical model. And then just recently, last year, we upgraded from POAMA to Access S1, and we started not only introducing monthly outlooks as well. So when I talk about seasonal outlooks, I'm usually talking about a three-month mean. And later this year, we'll start releasing weekly outlooks from that same model. And then perhaps another important thing that's happened recently is in 2017, CSIRO down in Tasmania began a research project focused on decadal climate prediction, and that's looking at next year and the year after. All right, so what I'll be focusing on, since this is a climate modelling winter school, is prediction with what essentially are climate models. They're coupled ocean atmosphere models. They also have land surface models and usually sea ice models included. And it's important that for prediction, it's not just the model that is required for a good prediction, but it's also the initialization, the initial conditions of that model, and how to generate that initial condition, which is what Craig will be talking about next, the data assimilation. And that is almost probably just as complex these days as the model itself to get those very good initial conditions. So we initialize at the Bureau in our current models. We initialize the atmosphere, the land, the ocean, and the ice, and we're getting that information from the observations, but we can't just hit the model with exactly what's observed, because the model will have imbalances, and so you have to kind of gently incorporate those observations into the model to get the best forecast, which Craig will explain. And then, so the forecast still depends very much on how well we can get that initial state. So, you would have heard earlier this week about, how the atmospheric model is developed. You would have heard about the ocean models, maybe the sea ice and land surface models. I'm not going to tell you too much about those here. Of course, you've already heard about them, but they're based on the equations of physics, and we use large computer simulations to do these forecasts. And the other important thing for climate prediction is having an ensemble of forecasts, and that's to represent the uncertainty and chaos in the system. So ideally, all these three parts are called the prediction system, but sometimes we get lazy and we just call the whole three components the model. But usually it's all of those components that are important. All right, so in Access S1, which is our current prediction system at the Bureau, if you look at what it's producing day to day, it does actually produce fairly realistic looking weather and ocean circulations. So it has an atmospheric resolution of about 60 kilometres in mid-latitudes, with 85 vertical levels in the atmosphere, and in the ocean has a 25 kilometre horizontal resolution with 75 vertical levels. And you can see the fairly realistic looking eddies that are produced in the ocean and the weather systems in the atmosphere. Now, even though I'm just showing Australia only here, for prediction on any time scales beyond a few days, really a global model is required because of the how information propagates around the globe for prediction. And so, obviously everything I show you today will be with global models. So model initialization, the model needs to have these accurate observations of the globe provided to it every day, the initial conditions. So this is just a schematic showing if we had the observations in red here in terms of an anomaly. Say this might be the ocean temperatures in the Pacific. This is the initial conditions, so this could have been a El Nino period. We initialize the model with these warm ocean temperatures in the Pacific, and then the forecast continues. All right, so importantly, we require good observations, not only of the current state, though, is we also need good observations of previous years, because we also run what are known as hindcasts. And these hindcasts, where we run the model based on initial conditions in the past to test the model, are very important for verification, knowing how well the model performs, but also for correcting model bias in our forecasts. So we're very much limited by these observations, especially of the ocean back in the past. And this is just an example of the observations that go into our model back in 2000 from the ocean, and then more recently in 2007. You can see how there's been a huge jump in the amount of observations of the ocean in that period, and most of that is coming from the system called the Argo floats. So these are autonomous, little, like miniature submarines about this long, about this wide, and they dive down in the ocean, recording temperature and salinity as they go, and they come back up, and then they submit that information back to satellite, and they'll be doing these probes of the ocean continuously. So yeah, for Access S1, we use past observations to run these hindcasts from 1990 to 2012. All right, so another important concept for this climate prediction or sub-seasonal to seasonal prediction are ensembles and probabilities. So as I said, we don't just run one model run out into the future, we run multiple to get an idea of how much, say, chaos is affecting our solution. And this is an example looking at Pacific Ocean temperatures, so the Nino 3.4 index, which is out in the Central Pacific, a good indicator of El Nino. And in this particular case, we just made an ensemble by perturbing the ocean and by very, very small amounts, by only 0.001 degrees Celsius, and seeing what influence that had on the prediction. And this is a very strong El Nino event, 97, 98, and you can see that even with such small perturbations in the initial condition, there was a growth in the error or the uncertainty into the future. So we're doing this every day, and in fact, we currently run with Access S1 33 ensemble members per day. 11 of those ensemble members go all the way out to 7 months, and 22 of those stop after about 40 days. And each of those ensemble members is started with slightly different initial conditions. We currently get our perturbations from an estimate of the uncertainty in the observations given looking at the differences in different reanalysis products. And then using that ensemble, we can provide forecast probabilities. So this is an example of the actual forecast for Australia that was released in late December last year for the 3 months, January through March 2019. And it's showing the chance of exceeding the median rainfall over Australia. And it's showing that, and where this is what the median rainfall is for that period, and it's showing that there's quite a lower than 50% chance in much of Australia for exceeding the median rainfall. So it was more like around 30% chance. So a much reduced chance of being wetter than normal. And this particular forecast verified fairly well over the Northern Territory and Western Australia and southeastern Queensland in this particular case. And here, even though we're only running 33 ensemble members per day, we're actually using 99 members lagged over several days to produce these forecasts. So it's a toss-up between having you want as many estimates of the future as you can, but if you lag too many days into the past, we are starting to use older initial condition information, which isn't ideal. Any questions so far? Nope. All right. So this is where to get your monthly to seasonal climate forecasts on the Bureau website. So this is the web address up here. Pretty simple, just /climate. And then once you go there, you go to Rainfall Outlook, and you can now select either the next 3 months or the months 1 and 2, say, or July or September individually. And this is the current forecast for July through September. So again, showing higher chances of drier conditions. And then also somewhat unique to this climate prediction game is that you can actually look at the past accuracy of the forecast. So this is telling us the percentage correct of these forecasts that we get from the based on all those hindcasts that we ran from 1990 to 2012. And we're getting to the time of year where the forecasts for rainfall are more kind of most accurate, and that's because of the influence of El Nino, Southern Oscillation, on Australian rainfall in winter through spring. It's got its strongest correlation with Australian rainfall that time of year, and that's when we get most skill from our dynamical model. So I guess climate prediction is somewhat unique in, say, what the Bureau releases to the public right now, in the sense that all our forecasts are probabilistic, and also we all provide this past accuracy information. You can't get that for the day-to-day weather forecast from the Bureau, and that's partly because the numerical weather prediction models don't have a long hindcast set for which to estimate that past accuracy. Any questions? No? Yeah.
So are you saying the skill improves if you're in a state of no interpretability?
I'm not sure I said that, so what? Yeah, ask you.
So were you saying that when you were in a state, a known El Nino state, your projections, your predictive skill was improved when you were in that state?
No. So okay, so you're saying we're in only kind of weak El Nino, or almost no state of El Nino right now, but this accuracy is computed based on all those hindcasts from 1990 to 2012. So that included all the El Ninos and La Ninas, right? And so we don't know. The only way you can do accuracy is based on many forecasts, and then the fact that but it is true that we tend to be more skillful if you only selected the El Ninos and La Ninas. We do tend to have more skill at those times, but there's more than just El Nino going on in the climate system that produces this forecast. So, we can't produce different maps depending on what state of El Nino we are in right now. Okay, different accuracy maps. So no, I don't think I was saying what you said. But thanks for the question. Yeah, so our probabilities up here are from the, if that was the median rainfall here, and this is now looking at rainfall instead of SST, then how many of those members were getting rainfall above that median? And this particular example, or this example here, is showing that many of the 99 members were actually below that median rainfall.
Could you talk a little bit more about how they've got that green plot there, which is saying something about accuracy?
Yep.
How does that work?
Oh yeah, so this is a very, very simple measure. It's not the best measure for a probabilistic forecast.
Right.
So what they do is they, if we were forecasting a less than 50% chance of above median, then we say just below median, okay? And if it was below median, we say tick. That's a 1. If it was above median and we're forecasting less than 50%, so we get a 0, okay? And then you add up all those 1s and 0s and divide by the total number of years, and you get a percentage. So this is saying that in that dark green, that in 75% of the hindcasts, we were on the right, our forecast was on the correct side of median.
Do you know the statistical significance of that? What's the chances of getting that if I just flip the coin?
The 75%?
Yeah.
Yeah, I think it's significant. So ideally we would have more years of hindcasts, but with Poama, the previous model, we did have many more years. So and it looked pretty similar.
Is that for 4 months a year? So we're talking 4 months a year times 12, so 4 times 12, 48 cases. Are we talking 12 cases?
Well, there were 23 years of hindcasts.
All right, okay.
So there's at least 23.
Right, 23
or potentially more, because we could have...
Yeah.
Okay. Yeah. Okay. And it makes sense physically too, because this is the time of the year that we know, based on 100 years observations, that El Nino has a pretty good relationship with Eastern Australian rainfall, and so it makes sense from our understanding. Okay. So as well as these forecasts just over Australia, the Bureau also provides forecasts of various indices of El Nino, such as the Nino 3.3, 3.4 or 4 indices, which are indices of the ocean temperatures, SSTs in the Pacific, and also the Indian Ocean Dipole, which is looking at the SST difference between the west and east of the Indian Ocean. And once again, it shows the ensemble members, as well as in the dark curve is the ensemble mean, the average of all those ensemble members. So as the previous question was about what current state we're in right now. So right now we're on borderline El Nino. Some of the ensemble members are taking us into El Nino, some aren't. So we're just hovering along this, about 0.8 degrees Celsius borderline El Nino conditions now and into the future. So forecasting these El Nino SSTs have generally been the kind of the gold standard for predicting climate on seasonal timescales, and it's usually the first thing that people who are doing climate prediction will look at when they develop a new global model. And here's an example that I got from it's a bit old now, but where there are various modelling centres comparing their forecast skill for this Nino 3 index on the left and Nino 4 index on the right here. And this is a correlation between what they predicted and what actually occurred. And also on this figure, so the higher numbers the better here. And also they're showing is the skill you would get just from persistence. So persistence is if we're at a value of, say, 0.8 degrees Celsius now, if we maintain that anomaly of 0.8 degrees Celsius into the future, how well would we do with that as a forecast? So at the moment, our official forecast from the model is pretty close to persistence. So persistence does it drops off more than the models. The models are actually beating persistence. Some of the models shown here are dark blue as an ECMWF. That's from the European Centre. The black here is POAMA, so our older model, and it's in the middle of the pack. And it's showing that once you go out about 6 months, if you do a correlation using all months of the year between what you forecast and what happens, the correlation is around 0.6, and that's significant. Although we've only got 82. There's a number of years in this forecast. We're looking at every month of the season. And so, for example, this is, as I said, it's the gold standard to look at because ENSO is perhaps the most important driver of climate variability on these seasonal timescales, and also because this is one of the most predictable things on that timescale in the whole climate system. So looking at this can help you feel better than, say, if you were looking at, say, temperatures averaged over Australia. So when we move from POAMA to Access S, that's one of the first things we looked at, and this is in the paper by Hudson et al. That I had as one of the 2 readings set for this lecture. And the POAMA, this is from 2 different initial conditions. Initial condition in February, where it's much harder to predict the Nino 3 into the future, and then from initial condition in August. These plots here we're using all months of the year. And we can see that POAMA, or Access S1, is beating POAMA with a higher correlation skill into the future. And this is a period of the year in February where we're heading into what's known as the predictability barrier or the persistence barrier, and the skill is a lot less, whereas if you start forecasts in August, you can see how well how much more skillful we are. At 4 months, we've got a correlation still of around 0.9. So here in yellow is what the Bureau currently issues. It has its day-to-day weather forecast at first 7 days, and then on the kind of the climate timescales, we issue a forecast for what we call season 1, which at the moment is July, August, September, and then month 1, July, month 2, August. But increasingly, users want a whole variety of timescales. And what we're moving to in the not too distant future is filling in the gaps between the weather forecast and the seasonal or climate predictions with products at these weeks 2, weeks 3, weeks 2 and 3 average together, weeks 1 and 4 average together. And this is all coming from the same model as these seasonal forecasts from Access S1. And then a little later on, they hope to also produce a forecast for what they call Season 2. And it's important to recognise what are the phenomena that are producing the prediction skill on these different timescales. Because there's no use giving a prediction unless there's skill, as Craig was suggesting at the beginning of the lecture. So at the very short timescales in that first 7 days in the weather prediction timescale, it's most in mid-latitudes. It's baroclinic instability that's providing our skill and also limiting it as we go further out. And then here are the various phenomena like the southern annular mode, Madden-Julian Oscillation that are providing skill on these longer timescales. And I have ENSO here in very big letters because it's in fact important all the way down to weeks 2 and 3, as I'll show later on. And then when we go further out, then these other phenomena such as the interdecadal Pacific oscillation or the quasi-biennial oscillation, which might be important for skill. And filling in these gaps between the seasonal prediction and the day-to-day weather forecast, so looking at, say, weeks 2 and 3, is being given the buzz phrase of seamless prediction. And it's this seamless prediction concept is blurring the scales blurring the distinction between weather and climate, and it's really what users want. Many users don't draw a line between the two, and in many ways, the modelling systems that we're developing into the future also provide no real distinction between what is weather and climate. You just simply start averaging over greater time periods as you go further out. And all right. So now, if we kind of go back here and start thinking about these sub-seasonal timescales, or these multi-week timescales, I've got the MJO, Madden-Julian Oscillation, as being one of the important drivers of the prediction skill on that timescale. So I'm just going to go through the MJO as an example of how it can provide some prediction skill and what we're doing with it in our modelling systems. So here's just some observations of the Madden-Julian Oscillation. So it is, so who in the audience has not heard of the MJO? Okay, that's good. All right, so the Madden-Julian Oscillation is these global scale circulation cells centered near the equator, and they propagate to the east with a period of about 30 to 80 days. So they repeat themselves after about a month or so. And along with it, there is tropical convection or rainfall that propagates to the east. And this is showing that where in this figure where time is going down and longitude is from on the x-axis. And the grey shading here is outgoing long-wave radiation from satellites. So where it's darker grey, it's probably indicating where there's cold cloud tops, deep tropical convection or rainfall. And here, in this particular point here on the 1st of December, and so these are averages from 15 south to the equator. So it's taking these strips around the globe each day and then lining them up with time. And time is going down. So here on the 1st of December, we're out near 80 east, that's the Indian Ocean. There was more clouds and convection than normal, and then it went dry, then it went kind of wet and cloudy again, then dry and wet and cloudy again, and you can see that with these sloping features in this diagram, that's eastward propagation of these cloud systems. And I'm also showing the winds that went along with it at the 850 hectopascal level, and you can see that the winds were westerly following the convection and more strongly easterly anomalies ahead of it. And so there are these circulation cells that propagate to the east. And as the Madden-Julian Oscillation, as these convective centres pass Australian longitudes at around 130 east, we often get bursts in rainfall in the far northern Australia. So this is simply the rainfall time series averaged over the top end during this period, and you can see that there was a lot more rainfall in mid to late December, then another burst in February, and another one in late March, and that lines up with these three events of the Madden-Julian Oscillation. So you can imagine that it provides some predictability on this multi-week timescale. And to kind of help understand that predictability and what it's doing on any one day, we at the Bureau have developed an index for the MJO, where instead of trying to look at plots like this to determine what the MJO is doing at any one day, we take all that information, the winds at the lower levels, upper levels, and the satellite OLR, using a lot of maths, in fact, empirical orthogonal functions, and decades of observations. We define an index for the MJO, and we can plot what that index is doing on any particular day. And so this is what the index looks like during this same period. And when here studying on the 1st of December, each dot here is an individual day, and when we have eastward propagation, you get an anti-clockwise circle in this phase space. It's projecting onto two EUFs of the computed from these observations. And so in this month of December, it goes about 3/4 of the way around the globe, then the rest of the way around the globe, February, and then March. So it ends here at the end of March. And when we have the dot, the index, in phases around 5 and 6, that's when we're more likely to get increased rainfall in northern Australia. So these phases simply track the propagation of the clouds and winds eastward along the equator every day. So importantly, we look at the prediction of this index directly out of our AccessS model. And this is an example from January 2018. So this is the light grey here were the observations of this index. Then this is the initial condition in the model. And once again, we have an ensemble of forecasts from that initial condition shown in the coloured curves. And then the dark black is the ensemble mean from these 33 members. And we can see that at this point here, we're in phase 5, where it should be probably starting to get rainy in northern Australia, and it forecasts further eastward propagation of the MJO into the future. And we can see we can use this index to measure how well we do at predicting the oscillation from our model. And we simply correlate these forecasts of the index with what actually happened with the index, the observations of the index, to give an indication of skill. So once again, this is a correlation skill, starting from a lead time of 0 days going out to 40 days. And what we did with our Poema model is in blue. What we did in our new model, the AccessS, or new system, is in red. And we can see that we have kind of statistically significant skill out to about 25 days in these, for the MJO in these models, and the AccessS was slightly better than Poema. So recently there was a case in northern Queensland where there were a lot of floods in early February this year, and the MJO had some role to play in those floods. And it did probably help to provide some week 2 predictability of these flood systems, even though in our monthly forecast we had very poor skill. So I'll just go back to what the Bureau currently provides are forecasts on these timescales. And back in, and they're usually, unfortunately, they're somewhat delayed. So the model runs might be around the 20th for this February flood case, around the 20th of January, and then they don't issue them until about the 30th of January for the month of February. And that particular forecast from the Bureau for the month of February in Queensland didn't show any real indication of those floods. And yet they were very devastating for the cattle industry in northern Australia. There was like 600,000 cattle that died. So this is just indicating that when we look at these shorter timescales, weeks 1, weeks 2, we did have a good indication of this rainfall occurring. So there was a high chance of being in the highest quintile. So quite, indicating that we may have had to have done something in terms of these floods at these timescales. But week 3, it really wasn't there. All right, and so if you look at the Hudson et al. Paper, you can look at how well the model does at various other modes of the system, such as the IOD and the southern annular mode. So Access S1 is a bit better than Poema in that for both these modes. And they've also gone through how well we do predicting over Australia in terms of rainfall, maximum temperature and minimum temperature. You can see green is the Poema model. Access S is the new model and system. You can see there's incremental improvements in most things over Australia, except there's some things that got worse. Obviously, Poema was, the amount of computing time that goes from Poema to Access was huge. The resolution was a big jump. And you make these huge changes in expense, but you really only expect incremental improvements. But nevertheless, Poema is very interesting to look at due to its long hindcast set. And in fact, I want to show you now some research that I did with Poema, which helps to understand the predictability on different timescales. So this is a paper we wrote called Seamless Precipitation Prediction Skill in the Tropics and Extratropics from a Global Model. And so what we did was we wanted to look at the prediction skill from the Poema model on all these different timescales. So to be fair across timescales, we increase our averaging window at the same rate as we increase our lead time. So this is the initial condition. So this, what I call here 1 day, that's the lead of 1 day averaged over 1 day. It's what others might call day 2. What I call 2 day is a lead of 2 days averaged over 2 days. So it'd be like days 3 and 4 averaged together. This one here is a lead of 1 week averaged over 1 week, or week 2. And I go all the way out to a 4-week lead averaged over 4 weeks, what others call month 2. And we're looking at precipitation around the globe, how well we can predict it. And so the Poema system was quite low resolution by today's standards, only T47, so that's like about a 2.5 degree horizontal latitude, longitude resolution. Had an ocean model and land. It was initialized with realistic atmospheric land and ocean initial conditions. We had a burst ensemble of 11 members each per day, and 3 versions of the model to provide 33 members, where we had forecasts or hindcasts from the 1st, 11th and 21st of each month out to 120 days. And we're going to compare those predictions of precept with actual observations from satellite from the Global Precipitation Climatology Project. And we can do it on the Poema grid. All right, and we're using, like I've shown you so far in this talk, correlation of the anomalies from the model with the anomalies from the observations. Okay, and the number of, for Craig, the number of the number of points going to each of these correlations. Throughout my December, January, February plots, there's going to be 117 values in the correlations, and in the JJL plots, that's June, July, August, 108 points. So this is the correlation of the anomalies for the, on top, the what is like day 2, so it's a 1 day lead, 1 day average, and this is like for month 2, 4-week lead, 4-week average, and on the left is for December, January, February. The right is June, July, August. So the top is like the weather prediction from the model. The bottom is the seasonal prediction, or the month 2 prediction. And we can see that on these short lead times, that there is a skill, over most of the globe. There are a few parts of the globe where there is a lack of skill, such as right here where it's blue. So red is good in these plots, blue is bad. And then once you get to these longer time scales, where it's got skill really concentrates down into the equatorial Pacific, and that's due to El Nino Southern Oscillation. However, other things you can get out of these plots is that if you compare DGF and June, July, August, you can see that in the extratropics, winter is more predictable than summer. And that makes sense given what we know about winter weather systems around Melbourne are generally more predictable than summer systems due to thunderstorms. So there's a bit more red here than there, and there's a bit more red here than there. And then in December, January, February, over Australia, we can see more skill more in Western Australia, whereas in June, July, August, there's more skill in Eastern Australia. And this is consistent with what we know about the El Nino linked with Eastern Australian rainfall. Okay, now looking at all those timescales in between, as I showed you on the first plot. So we're looking at the shortest timescale here in red and the longest timescale here in black, and going through the 2-day, 4-day, 1 week, 2 week, 4 weeks. And we can see, and this is a function of latitude for December, January, February on the left, June, July, August on the right. And we can see that the skill in the tropics actually, even though it starts off a little lower than the mid-latitudes, it is maintained into the future. Whereas in the exotropics, the skill drops away quite a lot from the near future to the longer leads. So really, on these longer lead times, it's the tropics that has the most skill and potentially can provide skill for potentially other parts of the globe if you get your teleconnections correct. And this is just showing it in another way. I'll skip that. So it's just demonstrating that the skill in the tropics overtakes the skill in the exotropics for about a 4-day, so towards the end of week 1 in December, January, February, and week 2 in June, July, August. So that's a 1 week lead and a 1 week average. And then we went on to compare that to another prediction system, much higher resolution than POAMA, the ECMWF model, and we also wanted to look at what we know as potential or perfect model skill. And that's in a more recent paper, 2017. And it includes an author from Frederick Vitar from the European Centre for Medium Range Weather Forecasts. So now we're also going to look at the ECMWF monthly system, which was operational in 2011. So it's much higher resolution. It's got a triangular truncation at 639 wave numbers, 62 levels in the atmosphere, and that very high resolution is run out to day 10, and then at day 10 they switch to a lower resolution of T319, but still much higher than POAMA, or even higher than what we're running in Access S right now. And they had 15 ensemble members and 4 hindcast start dates per year, on the 1st of February, 1st of May, 1st of August, 1st of November, at least in terms of what we analysed. And the POAMA as before, and comparing against these GPCP observations. Now we have many fewer values in these correlations I'm going to show you, only 48 values. And I'm looking at all year, not just summer or winter. So on the left of these columns is what we get from ECMWF. From the right, POAMA, same as what I showed you before. We can see that this high resolution model is definitely more skillful, especially at the short lead time. So this is the 1 day, 1 day, 1 week, 1 week, 4 weeks, 4 weeks. But they're both consistent in the sense that as you go to these longer lead times and averaging windows, the skill concentrates down into the tropics, especially the tropical Pacific, due to ENSO. Yeah. Okay. Another calculation you can do with these models is you forget about observations. You only compare, you assume that one of those ensemble members is truth, and you correlate all those, the ensemble mean from the other members with that truth. And I'll get on to what that really means. It can mean a variety of things, but this is often described as potential or perfect model skill in papers that have looked at this, using the assumption that one of the ensemble members is truth. And so, comparing to the previous plot, where we're correlating against what actually happened in observations, this is what we get if we just compare against one of the ensemble members. So E7WF is suggesting that we should be very predictable in this short time scale. But again, as you go further out, it should be the tropics, and especially the tropical Pacific, that has the highest predictability. And similarly for Poema. And also somewhat expected is that when you make this assumption, the models tend to be under-dispersed. So they usually always get better potential or perfect skill than they do actual skill. So if you go, the values here are almost always less than the values in this plot. So these 1 week and 4 week plots are similar shape to those for actual skill, with highest values in the Central Pacific. I said that. But the 1 day plots are quite different between E7WF and Poema, and also very different to the actual skill at those shorter lead times. So what does that mean? So possible interpretations for the difference between this potential and actual skill. One can be that, well, there must be room for improvement in actual skill. So that's what people hope for when they do these calculations usually. But it can also mean that simply that there's too little ensemble spread resulting in too high potential skills, so that you haven't perturbed your model ideally to get a good estimate of that uncertainty. And the differences could also just be because there are errors in the verifying observations which can artificially reduce the actual skill. And I'm almost getting to the end here. Actually, so has anybody got any questions about that? Maybe Craig is going to talk more about ensembles and...
Yeah, I mean, that was really interesting, the plot you showed, how different it was, if you pretend that one of the ensemble members is the truth. What we try and do with ensemble forecasting is make that true. And with a perfect ensemble forecast, there would have been no difference between those two plots.
Correct.
And as you pointed out, one of the issues is maybe the ensemble's not being initialized right, but the other one is the model error. We don't know how to characterize model error in the ensemble forecast. Ideally, you want to be perturbing each ensemble member as it marches along randomly. Right. With a mean zero. Yeah? Because there is unresolved processes that are doing stuff.
So, so in Poema, we did not do that, but in AccessS, we do actually have this stochastic
kinetic energy back
skeb. Yeah, which I don't know much about. But anyway, so as Craig said, that ideally, these two plots should look the same. That
close. You mentioned the observation error. That should be different only by the observation. But they look like they're a lot more different.
And so ideally, you want the root mean square error that you compute over many forecasts between your forecast and observations to be equal to the ensemble spread.
Spread skill.
It's called the spread skill relationship. Anyway, that's a very important thing to consider when you're building these prediction models, both on short time scales and long time scales. Okay, so to the near future of climate prediction at the Bureau, this is what we're running right now. We're very reliant. So this model was actually essentially purchased from the UK Met Office, and at the UK Met Office, it's called the Global Climate Model version 2. We're currently reliant on the UK Met Office for the initialization of the hindcasts. In real time, we're actually initializing the atmosphere from our local global access model.
But you have your Australian-made ocean data assimilation. So the ocean initialization is
in real time. Yeah, and then, but then as we go to Access S2,
All right.
it's going to be the proper BOM-developed ocean assimilation and initialization. Okay, I think he accesses on its foam. Yeah, yeah. So, but we're running this already, running the hindcast already.
Australian as well, isn't it?
Okay.
Yeah. Anyway.
All right. Yeah. So we've got only 23 years of hindcasts in that current system, which is a bit limiting. And as we go into the future, we're going to have 30 plus years of hindcasts, which is going to help a lot more. And one improvement is we're going to start initializing soil moisture. We weren't able to do that in Access S1. So even though it's going to be identical actual physical models, the initialization is going to be different, and actually the perturbations for the ensemble are going to be different, and also how many years of hindcasts are going to be different, which we'll also hope to incrementally increase our skill. And then when we move to Access S3, it will be a different model. So rather than GC2, we'll go to GC4 or GC5, and that will have completely different physical parameterizations, such as for convection, or we use a thing called CoMorph that is being developed in the UK with help from Australia. And it's going to have this also Bureau-developed weakly coupled assimilation and initialization, which I think Craig will know more about than I do. And we hope to have model improvements from projects we're doing in the Bureau right now. Yeah, so any questions about these models? And then I've only got one slide. Yep. What's your question?
Like we'll have two versions, one for research, one for prediction. What's the difference between them?
Sorry, are you talking about our models or someone else's model?
This model.
No, we have the same version. Well, in Poema, we did a lot of research experimentation where we would change something in the model to research what impact that might have on the prediction. So, for example, we might change the amount of ozone to see what that impact had on the forecasts, and that has been done a lot with Poema. With Access S, there's been less experimentation. I think it's Zoe who's in the room. You're doing experimentation with Access S?
Yes.
Do you want to summarize it?
I haven't saw that. I don't know.
Okay, so sometimes there is a different research version, but with Access S right now, we really don't have a different version. Okay, I hope that answers your question. And then, summarising. Key messages for climate prediction on these scales are you need good initial conditions, you need a coupled model, and you need appropriate ensemble perturbations to do it. We also need many hindcasts. That's where we do these forecasts using previous observations, and that's for verification and bias removal. And the lack of good ocean observations in the past limits that hindcast length. You need lots of computing. As we go further into the future, the distinction between weather and climate is becoming less meaningful, and that's just both for users and also in our modelling strategies. I know that many modelling centres that are doing numerical weather prediction are moving to coupled models from day zero. I think ECMWF is doing that now. So previously, one main distinction between weather prediction and climate prediction was whether you use an atmosphere only or a coupled model. But now everyone's going to use coupled models into the future. So that distinction is really becoming less and less relevant. And you also must know your limits to predictability. That's it.
Just with your seasonal projection of the NJO index, does that mean you're using seasonal projections of OLR to...
Prediction, not projection.
Projection of OLR to make the NJO index?
Yeah, so we're getting... we're getting OLR out of the model. as well as the winds at the 850 level and the 200 hectopascal level from the model, and projecting, oh yeah, that's the word projecting onto the EUFs. So we're taking that to get the index in real time, but we're taking the predictions of the OLR prediction of the winds and using that to compute the index into the future.
Then how come we can't just use the OLR to therefore make seasonal forecasts about the rain?
How come we can't just use OLR to
To tell you where there's
well, we can. Well, when the OLR is highly related to the rainfall, and the only reason why we're using OLR from the model to compute this index is because we had much longer observations of OLR with which to compute and create the index to start with. So just to be consistent with the index which was created from observations, we're using OLR from the model. But ideally, that this is just forecasting the MJO itself. If you want to know what precipitation is going to happen at your location, then you probably shouldn't use this, but you should actually look at the actual prediction coming out of the model at your location, and not try and make your own forecast on precip based on the index forecast. Does that answer your question? Yeah, so I think you're right. Yeah, you should just look at the precip itself from the model, or OLR. Yep.
Do you think that this model for the seasonal prediction, they are tightly coupled with the tropics rather than subtropics? Like extratropics?
What was it? Say again?
This model, they seem like they are tightly coupled with tropics rather than the extratropical systems. Everywhere you are having the ENSO features, ENSO kind of features in your ensemble mean, but not so extratropical variabilities.
I don't really understand the question.
I'll ask later on.
Okay. Did you understand? No? Okay. Okay, ask me later, sorry. I think it was something to do with these figures here, right?
Yeah. So everywhere you are having like this ENSO kind of signature, but not so much of extratropical variabilities.
Oh, so you're picking up the tropical variability, but not extratropical.
Yeah, well, that's simply because, how about we go the one with the ECMWF as well? Yeah, so it's simply just showing that where it's most predictable. It's not saying that there's no variability in the extratropics at those timescales. It's just that the variability on that timescale that exists in the extratropics is much harder to predict, or we can't predict it right now with our current models. Not as well as what we can right in the Central Pacific. It's not saying that that variability doesn't exist. It's just saying we can't predict it.
I'm just talking about the predictability of the variability, that you can predict quite well in the tropics, but not in the extratropical features.
Correct. Yes. And yeah, that's because El Nino, in terms of its sea surface temperatures and rainfall, the signal is very concentrated in the tropical Pacific. It also extends a little bit into the maritime continent, but every event is a little different, and model biases might be limiting on how well we forecast over the Indonesian region. Yeah.